Hi everyone, in this video our objectives are the following. Interpret heating and cooling curves. So I'm going to show you how to navigate yourself around a graph that represents either a substance heating up or cooling down. And that's going to be followed by identifying which heat formulas to use during various situations. So as a substance is heating, we could use a formula to calculate the amount of heat necessary for it to change phases or forms or just increase in temperature, and also the opposite as well. As things cool down, how much energy is going to be released as a substance changes forms or loses energy or temperature. So let's begin by taking a look at a heating curve. So here's our typical heating curve. There's time here on the x-axis, and this is depicting that as time moves on, there is a constant source of energy going into a substance. And the line here, the slopes, represent what is happening to the substance itself, temperature-wise, as it is absorbing this energy. So on the y-axis we have temperature in degrees Celsius. Keep in mind that could also be in K for Kelvin, because every time we move 1 degree Celsius we are moving 1 degree Kelvin. They just start at a different value, but considering a Kelvin works just as well. Something to note right at first is the substance is absorbing energy. So right off the bat we could consider this an endothermic change. If the curve were angled downward, that would be exothermic. So let's identify different locations on this graph. Between the point A and B, we say that this segment is a solid. Between segments C and D, it is a liquid. And between segments E and F, it therefore must be a gas. So, to take a look at what's happening here, as we move from this position, being a gas, to this position, we must notice, and let's see if I could coordinate this. We notice that as we go up the slope, we are also going up the temperature scale. So this is, I'm sorry, I said a gas. This is a solid. So this is a solid that is absorbing energy and its temperature is increasing, but it is still a solid. As we move forward, increasing energy, the substance is accepting more energy, absorbing it. Well, we notice that it goes from segments B to C. But is the temperature increasing? It is not, because the particles themselves are actually just rearranging. So the energy that is being absorbed is being used to rearrange the particles within the substance. And only when it reaches this point here, and again that's C, reaches point C, all of the solid has converted to liquid. Then at this point, as it absorbs more energy, it could then increase the temperature until we reach this point. Now at this point, we've got the liquid as hot as it can be before it will start transitioning into a gas. So the energy that is now being absorbed is being used to rearrange the particles so that they are in the form of a gas. Once we reach this point, and this one is E, well, converting to gas has been completed. Now the energy that's absorbed is being used to increase the temperature of that gas. So that's how to read this. Let me also give you a couple of other key vocabulary terms here. When we go from D to E, we call that vaporization. And we could also say boiling. When we go from B to C, we could say that's fusion, or we could say melting. And now let's reverse it. If we go from E to D, we could say that that is condensation. And let me change the color of the pen so you could see from C to B what that is. When we go from C to B, we could say that that's solidification because it's becoming a solid. Solidification. And we could also call that freezing. All right, so let's take another one that is already labeled for you, I should say. So here's another one that is labeled. This time they're saying heat absorbed, where our previous picture said time, so it's heat absorbed over time. And again, this one's labeled for you. If this one's cleaner and easier for you to take notes off of, by all means pause. I'll show you another one in just a moment with a little bit more labels. And actually the moment's right now. Now here's just another graph showing virtually the same thing. What I like here is it's noting if this was water, that ice would transition from solid to liquid at 0 degrees Celsius, and it would transition from liquid water to gas at 100 degrees Celsius. Another thing that needs to be noted here is this happens under the same conditions of pressure. The pressure is not changing whatsoever. Now, in a later unit, we will learn that, well, boiling points are dependent on the pressure for which a substance is placed under. I will even show you how I can boil water at room temperature. So let's move on to another slide. And I put this one together to show you an exothermic reaction, because as time is proceeding to the right, heat is being lost. So we can call this right off the bat an exothermic change. And this is considered a cooling curve. And what I've noted for you here is the point in which a gas transitions to a liquid is right here. And if it were water, that would be at 100 degrees. Because if at 100 degrees Celsius it transitions from a liquid to a gas, when you give it energy, when you take energy away, it also happens at 100 degrees. So right down here, liquid will transition to a solid, so if it's water, it freezes and becomes ice at 0 degrees Celsius, only if you are removing the energy from the substance. Now these two other numbers here are related to Kelvin, and if you notice that if we assign 273 Kelvin to 100 degrees Celsius, if they both increase at the same pace, 373 Kelvin would be equivalent to 100 degrees Celsius. All right, so let's continue more and take a look at how to calculate how much energy a substance needs to have placed within it to transition from one position on this, well, now let's call it a map, on this map to another position. So now let's look back again at one of the heating curves and look at the position between D and E. Now there might be a question that asks, how much energy is required for a substance to absorb, to change from liquid, let's just say water, liquid water, to gas water at constant temperature, meaning the temperature would not be changing. And for that, some smart guy years ago devised a formula that matched what nature does. And he said Q, which is energy, is equal to M, which is mass, times HV, where HV is the heat of vaporization. Now, it's important that I show you this formula first because of that word vaporization. We know that when something becomes a gas, it's a vapor. So we would use this formula when you could identify on this graph, now called a map, that we are talking about this segment from D to E. Now, a little bit more about what the word or the term heat of vaporization actually means. And it means the amount of heat necessary to convert 1 gram of water, to convert it from liquid to gas. So, that is a value that has been calculated years ago through experimentation called a constant. So that value for water will never change. It is represented on our reference tables, and in a moment I'll show you where all the constants are that you will need for the future. Moving on to the next slide. Here we are talking about a question that might ask how much energy is required to add to ice at constant temperature, or ice to convert it to a liquid at constant temperature, where again Q is equal to energy, M is equal to mass, and HF is equal to what's called the heat of fusion. Now, if in fact here is vaporization, this one must be fusion. Okay, that's important to note. And similar to the definition for heat of vaporization, heat of fusion is the amount of energy necessary to convert 1 gram of water, 1 gram of ice, to 1 gram of liquid water at constant temperature. Again, that's a constant that I'll show you in just a little bit. Now, we also have an equation for when a question asks you to transition from C to D. Now, notice, when it goes from C to D, climbs to D, the temperature is increasing. So we have a formula that identifies this. So we have Q, energy, is equal to mass, times C, more about that in a moment, delta T, which is the change in temperature. So as the temperature climbs. So we have to note that change in temperature is related to the T final minus the T initial. All right, and that would get you the difference in temperature, the change in temperature. Now back to that thing called C. That's called the specific heat capacity. It too is a constant, and it defines how much energy is necessary to raise 1 gram of water 1 degree Kelvin. Again, this says Celsius, doesn't matter, it could just as well be Kelvin. Let me show you on the reference tables where to find these constants. So here is the first page of our reference table, and it shows you quite clearly in here what the constants are. So let me make this bigger. Our heat of fusion, being right here, is defined as 334 joules per gram. So joules, a measure of energy. So you need 334 joules for every 1 gram of water that is going to be melted, or for that matter, even frozen, because either it's absorbed or released, the energy that is, but it's 334 joules per gram. Here's our heat of vaporization, 2,260 joules per gram, again to convert water to gas or even back from gas to liquid. And here's our specific heat capacity, 4.18 joules per gram degree Kelvin. Now, if you do forget the formulas, you would just go to the back page of our reference tables where it's actually depicted for you right here in this area for heat. Here are your formulas. Hope this helped.